For us to even know anything about light, we need ways of making it, measuring it, and using it. In order to do all of these things, we, creatures made of matter, need methods of interacting with light. We know that matter is somehow responsible for the creation of photons. But until now, we really haven't considered how. Light production falls into two major categories: incandescence and luminescence. Incandescence is the production of light by any body that contains heat energy, the energy of vibration. Incandescence is how filament light bulbs produce light. By warming the metal filament inside the light bulb using electricity, the metal grows hotter and hotter, emitting more and more light as the temperature increases. The scientific principle of black-body radiation explains how photons are created by the intense vibrations of atoms and electrons at high temperatures. Black-body radiation applies to any object above absolute zero, even those that are very cold, since even small atomic vibrations exist above absolute zero, the coldest possible temperature. The theory of black-body radiation describes how the oscillation of atoms in objects creates light waves. Atoms and electrons sloshing back and forth due to thermal vibrations or heat act as tiny emitters, creating oscillating electromagnetic fields. This wiggle of electromagnetic field can be wrapped up in a neat little bundle we call a photon. Luminescence is the production of light through atomic transitions, which are sometimes called cold body radiation. In the planetary model of an atom, electron orbits move in orbits around the nucleus. When an electron jumps from one orbit to another, it emits or absorbs a photon of specific energy to do this. There are many subcategories of luminescent processes. Fluorescence converts UV photons, which we can't see, into visible light. Photophosphorescence releases energy stored in glow-in-the-dark objects. And triboluminescence produces light when we chew on hard candies like lifesavers. Now that we've got some light to work with, let's make sure we can measure its properties. When we want to take a measurement of light, what are we measuring? We know that the speed of light is denoted by the letter c and is a constant, at just under 3 × 10⁸ meters per second. What is left is either a measure of wavelength, the frequency, or the energy that the photon packets carry. A typical red laser emits a beam of photons with a wavelength of 650 nanometers. It could equally be advertised as having photons oscillating at a frequency of 460 terahertz, or even in terms of the photon energy, 1.9 electron volts. Electron volts may sound like a strange unit. One of many we'll come across in this course. It is defined as the amount of energy that is gained or lost by the charge of a single electron moving across an electric potential difference of 1 volt. It is a minuscule amount of energy, equivalent to about 1.6 × 10⁻⁹ joules. The naming and labeling of light can be confusing. The thing to remember is that a photon's energy wavelength, and frequency can all be considered as equivalent ways to describe light. While a radio frequency photon emitted by a radio station is usually characterized by its frequency, say 102.9 MHz, an X-ray photon is usually characterized by its energy, say a kiloelectron-volt. Visible light photons are often described by their wavelength, between 400 and 700 nanometers. If you are given one of energy, frequency, or wavelength, there are some very simple mathematical relationships that allow you to determine the other quantities. The equation relating frequency and wavelength of a photon to the speed of light is the wavelength lambda times the frequency f is equal to the speed of light c. Let's double check the values we had for our red laser. We've been given its wavelength as 650 nanometers, so to determine its frequency, we simply divide the speed of light c by the wavelength lambda. Remember, in order to calculate this properly, we need to express both the speed of light and the wavelength in the common unit of meters. So a red photon with a wavelength of 650 nanometers has an oscillation frequency of 460 terahertz, exactly what I stated before. How much energy is our 650 nanometer photon carrying? Let's use our last answer of 460 terahertz to calculate the photon energy. This time, we need another simple equation that relates the frequency of a photon with the energy that it carries. The photon energy is given by the equation E equals h times f. E stands for the energy, and f stands for the frequency of the photon. But h is a new value in this equation. This h represents Planck's constant, named after Max Planck. It relates the frequency of a photon with its energy. H has a value of 6.626 times 10 to the minus 34 in units of joule seconds. So now our 650 nanometer wavelength photon, which oscillates with a frequency of 460 terahertz, carries with it an energy equal to 3 times 10 to the minus 19 joules. That is a tiny amount of energy. Each and every 650 nanometer wavelength photon carries an incredibly small amount of energy. But bright light sources, like lasers, produce tremendous numbers of photons, which is why they pack enough punch to damage sensitive tissues like the retinas of our eyes. Hence, the laser safety label that is a common phrase in laser labs: do not look into the laser with your remaining eye. The relationships we have discussed here can be summed up in just 3 equations. The first 2 we used, that we just ran through, and a combination of them. E is equal to hc over lambda. These simple relationships are modern discoveries, relatively speaking, since they were developed in the early 20th century during the quantum revolution. With these 3 equations, a technological revolution occurred that permitted the development of advanced optics and telescopes capable of measuring light from even the far reaches of the cosmos. The speed of light is known to incredible precision. Since the speed of light is well known, it has become common for astronomers to measure enormous distances in space in terms of the time it takes for light to travel in a given amount of time. For example, the distance that light can travel in 1 second is known as a light second. 1 light second is equal to 299,790,000 metres, or 299,790 kilometres. A number this large can be hard to wrap your head around, so let's compare this distance to one we can imagine, the distance from the Earth and to the Moon. The distance between the Earth and the Moon is 384,400 kilometres, which is just a bit larger than 1 light second. We could use the unit kilometres, which is getting a bit crazy at this point, or we could use the unit of light second. In this new unit, the distance between the Earth and the Moon is 1.3 light seconds. In other words, it takes a photon of light 1.3 seconds to travel from the Earth to the Moon. If we now step up the size scale and consider the Earth and our Sun, it takes light 8.3 minutes to travel from the Sun to the Earth. So we say that the distance is 8.3 light minutes. Since the distance from the Earth to the Sun is so important in astronomy, astronomers also introduced a new distance called the astronomical unit, abbreviated to AU. An astronomical unit is the average distance between the Earth and the Sun and is equal to 8.3 light minutes, or 149.6 million kilometres. Yep, the measure of the distance in kilometres is starting to get a bit crazy and messy. If we return to the speed of light measuring stick and continue to shift the size scale further, we have had light seconds and light minutes, and then a light year is the distance light travels in 1 year. 9.5 times 10 to the power of 12 kilometres. A light year sounds like a big distance, but the distance between the Sun and the next closest star, Proxima Centauri, is larger than this. Proxima Centauri lies 4.2 light years away. The distance to the centre of the Milky Way galaxy is close to 25,000 light years. The final unit of distance we want to mention here is called a parsec. This distance is equivalent to 3.26 light years and was defined in 2015 to be equal to 648,000 divided by pi astronomical units. This unit of measurement, developed in the early 1900s, may sound familiar to some of you, from the beloved character in Star Wars, A New Hope. Han Solo, owner of the Millennium Falcon, brags to Luke Skywalker and Ben Kenobi that it's the ship that made the Kessel Run in less than 12 parsecs. On first hearing this, you might think that a parsec is a measurement of time, but this is obviously not the case. According to fan theory, the Kessel Run is a heavily used smuggling route that normally takes 18 parsecs to navigate. However, Han claims he had shortened the journey by skirting a nearby black hole cluster called the Maw. This path took him closer to black holes than others were willing to go and shortened their route by 6 parsecs. However, in the original script written by George Lucas, Han's line is to be delivered in such a way as to denote he is obviously lying, in order to boast in front of Luke and Ben. Needless to say, the Millennium Falcon did prove to be a fast ship. And the way speed is portrayed in these films depends not only on visual effects, but also on sound effects. Yes, you heard that right, the Doppler shift.